All right, this video is chapter 10 takeaways for gases. So first important thing we need to talk about is that gas pressure is caused by collisions among molecules. And so we can almost relate everything back to why does the pressure change, and it has to do with the collisions changing. So, if the pressure increases, it's because the number of collisions among molecules has also increased. And maybe that's from a change in temperature or from a change in volume. It doesn't really matter. It's just that we can relate it back to a change in collisions is going to cause a change in pressure. We know that pressure has many different units. Most common, ATM, kPa. We know it can also be in torr, millimeters of mercury, PSI if we're talking like tire pressure, and we know we have conversions to convert between those units. Okay, so from there, we talked about STP, or standard temperature and pressure, which is just a set of conditions. So of course 0 Celsius is your standard temperature, and 1 atm is your standard pressure. There's also the conversion that says that only at STP, 1 mole of a gas occupies 22.4 liters. And that's that idea of molar volume. Okay, but that's only, oops, it looks like I marked through that. It's only at STP. So that this is where we've learned that if I have a gas that's not at STP and I'm interested in finding moles, I'm probably going to have to use the ideal gas law, and I'm not allowed to use this conversion unless the container or the gas is at STP. So it's very important to know. That's definitely a takeaway point. From there, we talked about all the different gas laws. There's no need to memorize them because they're given to you. But probably the most important ones are the combined, which we did do some discussing about how all the other smaller gas laws like Boyle's law and Charles' law are contained within this combined gas law, right, that relates the pressure, the volume, and the temperature. So that's the combined. We know our favorite that we use all the time is the ideal gas law. PV equals nRT, of course, where R is the constant. Again, no need to memorize because you'll be given those values. We also have Avogadro's law, which has no formula, but it says at equal temperature and pressures, equal volumes of gases contain equal molecules. And that's where the whole balloon discussion comes into play, where I would draw the balloons and we would talk about, which balloon is heavier, which I will do that in a minute. But that's the law that kind of doesn't have a formula, so to speak. We also know that the ideal gas law can be used in a couple different ways when we talk about partial pressures and total pressures. So we know that we can take the ideal gas law and solve for the total pressure in the container, but I would have to know my total moles. And then I can also solve for the partial pressure of some gas, call it gas 1, but I would have to know the moles of gas 1. And I guess there is one more formula, which is that whole mole fraction formula that says the partial pressure of one gas divided by, that was a P. The total pressure is equal to the moles of the first gas divided by the total moles. Okay, so, but more important than that is the relationship among the variables. And this is that whole discussion of who's directly proportional and who's inversely proportional. So we know that if we decrease the volume of a container, the pressure will increase. So that's inversely proportional. And it's also so much so, like we've talked about before, that if we were to divide the volume in half, the pressure is not only going to increase, but the pressure is going to double. So keep that in mind when we're talking about these relationships. Volume and temperature are direct, so volume increases, so does T, right? Or we could say volume decreases, temperature decreases. And P and T are the same way. So pressure increases, temperature increases, or decrease and a decrease. We have a couple more. We can say moles of gas. If it increases, then our pressure is going to increase. What else? Am I missing something? Maybe that's it. And also, we need to keep in mind that our temperature is always in Kelvin. Okay. Let's see. Okay, and then we have the idea of effusion and diffusion, which is a discussion of the movement of gases. We know that less massive gases move faster, but we've also learned that the bigger discussion is how much faster, and that's where this formula comes in. This is the rate of gas A over gas B is equal to the square root of the inverse of their molar masses. Looks like this. And remember, I always say put the how do I want to say that? The quickest moving gas should be A in this formula. And that's only because then this rate over here would come out to be like, 3 to 1 or 4.2 to 1 or something like that, instead of something funky like 0.2. So that's effusion and diffusion. And then basically the only other thing I said I would do were the balloons. So this is where, this was a kind of a discussion of all these ideas rolled into one, where if I had 4 balloons, say, I don't know, H2 into helium and, I don't know, carbon dioxide, all gases, and we'll say P, T, and V are all equal. Okay, well, think about, this is something that I don't know if I've come out and mentioned. If P, V, and T are all equal, think about solving ideal gas law. Well, if P, V, and T are all the same for these 4 balloons, we know R is a constant, it means N is the same, right? So keep that in the back of your head. If the pressure, the temperature, and the volume are the same, then I have equal moles. Okay? If I have equal moles, I have equal molecules. Okay? Now, I'm not going to have equal masses because their molar masses are different. And I'm not going to have equal atoms because we know in this case I have 3 atoms in a molecule. This is a atom, so this one is the least number of atoms, and then these two have 2 atoms for every molecule. Okay, so if I had to answer the question of which balloon would weigh the least, it would be H2, right? Because it's the least massive in terms of its molar mass. CO2 would be the heaviest. We could answer like which balloon would stay inflated the longest, right? That's a good question. That goes back to this effusion and diffusion, right? The gas who's the lightest is going to escape the balloon the fastest, which means the balloon filled with H2 is going to deflate much quicker than the balloon filled with CO2. So the CO2 balloon is going to stay inflated longer. However, all these balloons have equal moles of a gas inside. And if we were given P, T, and V, we could calculate that. So I think that's it for the main ideas in the gas chapter. Yeah, so those are your takeaways for chapter 10.